Hi everyone and welcome to this new video about AC steady-state power analysis. This is our example number 4. In this example we will look again to a RL circuit. In this case we have a little bit complicated example compared to example number 1. We have two inductors L1 and L2, one resistor and one voltage source Vs, and the values of these elements are shown here. And we would like to calculate again four parameters, which are the apparent power, the real power, the reactive power, P, S, P, Q, and also the power factor for the complete circuit. Now, as we know from the previous examples, we started with the drawing of the power diagram that will allow us to see where we have to go, where we're heading. That will also illustrate this concept in more detail. So I will also do that here very briefly. So the power diagram. We make a sketch, and since we know this is the inductive system, we already know that the Q or the reactive power will be in the positive Y direction. So that's actually one important information. So the R, or the real power P, the total, will be in the plus X direction and the Y direction, plus Y direction. We will have the reactive power, and that will be, of course, again vectorially summed to the apparent power, and there is also a phase between the S and the P that's given by theta, and if you know the theta you can calculate the power factor PF. Okay, let's again look at the total impedance. First I will denote this point, this node here, as point A. So the impedance I'm looking here is the following: Z is equal to L1, the reactance of that, so XL1, plus the impedance seen at point A downwards. So actually this complete impedance. So I will make this also, I will denote this also by a new name. So I will make here, so I will reduce this to one impedance ZA. So ZA, I will make this in red. This is actually what I need to calculate. What is ZA? ZA is the parallel combination of R and the XL2. So I need actually XL1 and XL2, as you can see from these expressions. So let's calculate that also here. So XL1 will be omega times L1, and omega is 400, which is in the expression of Vs in the voltage source, and the value for the L1 is 0.02. So let's substitute it also here, which will give us 400 times 0.02 is 8 ohm. For XL2 is the similar procedure, omega times L2. Omega is still 400, that doesn't change, and we have now 30 millihenries will be 0.33. It will be 12 ohms. Okay, now that's actually for the reactances of the inductors L1 and L2. Okay, let's move on with this calculation for ZA. Now, you can write it down in a different form, with multiplication and divided by the summation of these two components, which is J times R times XL2 divided by R plus J XL2. Now, you already know all of the components now here, so that's 10 for R times 12 for the XL2 divided by 10 plus J12. It will be J120 divided by 10 plus J12. If I now simplify this a little bit, so I will have ZA is equal to divided by 2, so I will get J60 divided by 5 plus J6. That's actually the reduced form of this. And if I now use again complex conjugate of this term, and I multiply both of the sides of this expression, I will get the following: J60 times 5 minus J6 divided by 5 plus J6 times 5 minus J6. That's actually what you do to have a real expression in here. So what you have is the following: you have the 360 minus j 300 divided by 5 squared plus 6 squared. Now if you work this out, you will get the following expression: 5.9 minus j 4.9, and it will be in ohms. Okay, this is actually the expression for ZA in rectangular form. I will keep it like this. I will not go to the polar notation, which is not required at the moment. Why? Because I would like to add the ZA to the expression for the XL1. So for addition and also for subtraction, we also discussed this in another video about phases and complex numbers. You would like to keep it in the rectangular form. So what do I have? Then the following. I can say the following: Z is equal to 8, which is already calculated, plus 5.9, J8 of course, because it is a reactive part. So J8 plus 5.9 minus J4.9. And this will be reduced to 5.9 plus J3.1 ohms. Okay, that's actually the situation here. So again, for the complete circuit, for the complete system, this is the real part. So this is the real, and this is the imaginary. So this is the total impedance in real and imaginary parts expressed here. Now if I make a drawing, it will help also for the impedance. So let's make an impedance diagram. So impedance diagram. So how does it look like? Again, we are in the positive side of the phase, so I will have the real part here and an imaginary part there. So there is the real part, which is 5.9 long, and there is also the imaginary part, which is 3.1 J 3.1, and the summation of this vectorially will produce the value of Z. And this angle, again, between the Z and the 5.9 is theta, and is again the same theta as we have calculated if you calculate from this expression. So we need to do that, of course. So what do I have? I have the rectangular expression. If I now go to the polar notation for this, I will have Z is equal to 6.7 and then phase 28 plus 28 ohms. So this is the phase is 28 and the Z absolute value of that, or the magnitude, is 6.7. That's actually the whole issue about the total impedance. Now we require the total impedance. Why? Because we will also like to go to the total current supplied by the voltage source. So the total current by the voltage source, IS, in RMS, of course, that is required to calculate the powers, is equal to the V source in RMS divided by the total impedance seen by the source. Now, since we know that the VS RMS is equal to the VS amplitude of that divided by the square root of 2. Now, the value of the amplitude for the voltage source is 60. So if I do that, 60 divided by the square root of 2, 60 divided by the square root of 2, I will get 42.4. And since we work in the phasors, we're using phasor notations, and this has a phase orientation of 0 degrees, so I can use the magnitude of 42.4 volts and phase 0 degrees. So I can now calculate the IS in RMS, which is equal to 42.4 phase 0 degrees divided by 6.7 phase 28 degrees. And this will bring us to the value of 6.3 phase minus 28 degrees in amperes. So I can already see what the value here is. So for this, and this will be a lagging power factor, because the current, the phase of the current, the total current, has a negative sign. It's actually very important. So I already know that the power factor will be lagging. Okay, now the powers, this is actually the next step. So let's calculate the powers for the complete system, for P and the Q and the S. So there's actually this diagram. I would like to calculate the elements in this diagram. So let's move on. So powers. What is the P? So what is the real power? The real power P is equal to the source current in RMS squared times the real part of Z. And for real part of Z, you can look at a rectangular expression. So it is actually 5.9. And for this, you will take the amplitude of the RMS value of the source current, and we don't bother about the phases. So what we have is the following. This is 6.3 quantity squared times 5.9. That will result in 234 watts. So I will also do Q, which will be also the source current RMS squared, and it will be the imaginary part of the impedance total, which will again be 6.3 squared for the current, but this time we will take 3.9 because that's the imaginary part of Z. And this will result in 123 volt amperes reactive. So if you now express this completely in vector form, I will have S is equal to 234 plus J 123 volt amperes. And if you convert this to polar notation, you will have 264 phase 28 degrees volt amperes. And note, we have again 28 degrees as we had for the impedance phase. So the phase for the impedance and phase for the apparent power will be exactly the same. And then finally, the power factor, that's actually the final calculation. The power factor, which will be lagging, we already know. So power factor PF will be cosine of theta and will be lagging, we already know. So let's substitute the value. So it's 28 lagging, and that will result in 0.88 lagging, and that's actually the power factor, and that's actually also the last unknown for this example, and that's the complete procedure for this circuit. Again, it is not complicated if you just recognize that you can reduce this parallel combination to one impedance, and the procedure is exactly the same as actually for example 1 and other examples. So I will see you next time also for other examples, and keep in touch and have a nice day.